Hello, Lonnie Decker and myself, Elaine Horn, would like to share this presentation with you on multi-area OSPF. The presentation will be broken into 3 recordings. Part 1 of the recordings will include a review of OSPF single area. Part 2 of the recordings will include multi-area OSPF implementation and the types of LSAs exchanged between areas. Part 3 will include configuring multi-area OSPF version 2 and OSPF version 3, verifying an OSPF version 2 and OSPF version 3 configuration, and a review of the OSPF key points. OSPF version 2 is used for IP version 4 network addressing, and OSPF version 3 is used for IP version 6 network addressing. It is important that you understand OSPF single area concepts and configuration before beginning the study of multi-area OSPF, and that is the reason that we have decided to include this review as part of the presentation. As a review, OSPF, Open Shortest Path First, is a link state routing protocol with an administrative distance of 110. It is a classless routing protocol, therefore it supports VLSM and CIDR. OSPF quickly propagates network changes. Routing changes will immediately trigger OSPF routing updates, so it is more efficient than distance vector routing protocols such as RIP version 2. RIP version 2 uses periodic updates of every 30 seconds. In OSPF, the cost of a link is based on bandwidth only. Higher bandwidths will have a lower cost. OSPF creates and maintains 3 databases. The first database is an adjacency database, which creates the neighbor table. Then there's the link state database, which creates the topology table, and a forwarding database, which creates the routing table. These tables contain a list of neighboring routers to exchange the routing information with and are kept and maintained in RAM. Once the network is converged and all routers in an area will have identical link state databases. OSPF uses the shortest path first algorithm to choose the best path. The CPU processes the neighbor and topology tables using Dijkstra's OSPF algorithm. This algorithm is based on the cumulative cost to reach a destination. The SPF algorithm creates an SPF tree by placing each router at the root of the tree and calculating the shortest path to each node. The SPF tree is then used to calculate the best routes. OSPF places the best routes in the forwarding database, which is used to make the routing table. OSPF uses link state packets to establish and maintain adjacencies and exchange routing updates. LSPs represent the state of a router and its links to the rest of the network. OSPF exchanges messages to convey routing information using 5 types of packets. These packets are hello packets, database description packets, link state requests, link state updates, and link state acknowledgments. These packets are used to discover neighboring routers and also to exchange routing information to maintain accurate information about the network. Let's look at the hello packet shown in the graphic. The OSPF type 1 packet is the hello packet. Hello packets are used to discover OSPF neighbors and establish neighbors adjacencies. and they advertise parameters on which two routers must agree to become neighbors. Hello packets are also used to elect the designated router and backup designated router on multi-access networks like Ethernet and Frame Relay. Just a reminder, point-to-point links do not require designated routers or backup designated routers. The figure displays the fields contained in the Type 1 Hello packet. Important fields shown in the figure is the type. It identifies the type of packet. A 1 here indicates a hello packet. A value of 2 would identify a database description packet. A 3, a link state request packet. 4, a link state update packet. And 5, a link state acknowledgement packet. You also notice that there is a field for the router ID. This is a 32-bit value expressed in dotted decimal notation used to uniquely identify the originating router. It will have the same format as an IP version 4 address. There's also an area ID. That is the area from which the packet originated. A network mask, which is the subnet mask associated with the sending interface. A hello interval, which specifies the frequency in seconds at which a router sends hello packets. The default hello interval on multi-access networks is 10 seconds. The timer must be the same on neighboring routers, otherwise an adjacency is not established. There's also a field for the router priority. This is used in the designated router and backup designated router election. The default priority for all OSPF routers is 1, but this can be manually altered from 0 to 255. The higher the value, the more likely the router becomes the designated router on the link. The dead interval is the time in seconds that a router waits to hear from a neighbor before declaring the neighboring router out of service. By default, the router dead interval is 4 times the hello interval. This timer must be the same on neighboring routers, otherwise an adjacency is not established. Notice there is a field for the designated router. This would be the router ID of the designated router. The backup designated router, again, this would be the router ID. And then finally, a list of neighbors, and this would be a list that identifies the router IDs of all adjacent neighbor routers. Type 4 are link state update packets, and they are used to reply to link state requests and to announce new information. Link state updates can be one of 11 different types of link state advertisements. In fact, sometimes link state updates are sometimes referred to as link state advertisements. Notice sometimes they're used interchangeably, the two words. Only the first 5 link state advertisement types are covered on the CCNA. So if you look at the chart here, types 1, 2, 3, 4, and 5 are the ones that will be tested on the CCNA and will be covered in our discussion of multi-area OSPF. This is a basic single area OSPF configuration. Interfaces are configured. So you see those configured right here. And then networks are advertised. So the networks are advertised down here. The wildcard mask, this part of the command here, is used to identify which bits in the network addresses are significant. The network 172.16.1.16/28 will be advertised as 172.16.1.16 with a wildcard mask of 0.0.0.15. This wildcard mask is the inverse of the subnet mask, which is 255.255.255.240. Notice the subnet mask for /30 is 255.255.255.252, and the wildcard mask used to advertise this network is 0.0.0.3. A shortcut for calculating the subnet mask, if you've forgotten it, is to subtract the subnet mask from 255, 255, 255.255. So if you would do that calculation here with this 255, 255.255.252, you would end up with 0.0.0.3. We keep talking about the router ID, so that must be a pretty important portion of OSPF. So every router requires a router ID to participate in an OSPF domain. The router ID can be defined by an administrator or automatically assigned by the router. The router ID is used by the OSPF-enabled router to uniquely identify the router and/or participate in the election of the DR and BDR. Let's review how to determine the router ID. As illustrated in the figure, Cisco routers derive the router ID based on one of the three criteria in the following order. The router ID is configured using the OSPF router ID router configuration mode command. The router ID value can be any 32-bit value expressed as an IP version 4 address. This is the recommended method to assign a router ID. If the router ID is not configured with the router ID command, the router chooses the highest IP version 4 address of any configured loopback interfaces. This is the next best alternative to assigning a router ID. If no loopback interfaces are configured, then the router chooses the highest active IP version 4 address of any of its physical interfaces. This is the least recommended method because it makes it more difficult for administrators to distinguish between specific routers. Here is a sample configuration of a router ID. So you're going to notice the first thing they did is they put in the loopback, but after they put in the loopback address, they decided that they would specify the router ID. And notice again, it looks like an IP version 4 address. Once a router ID is set, you will need to either reload the router or use this clear IP OSPF process for it to take effect. Notice the router ID can be verified with the show IP protocols command. So you can see it being verified down here, and the router ID is 10.1.1.1. OSPF uses cost as a metric. A lower cost indicates a better path than a higher cost. A 10 megabit per second Ethernet line has a higher cost than a 100 megabit per second Ethernet line. The formula used to calculate the OSPF cost is cost equals reference bandwidth divided by interface bandwidth. The default reference bandwidth, if you look over here in the table, is 10 to the 8th, which you'll see right here. Therefore, the formula is cost equals 10 to the 8th divided by the interface bandwidth in bits per second. If you refer to this table, you can see a breakdown of the cost calculation. Notice that fast Ethernet, gigabit Ethernet, and 10 gigabit Ethernet all share the same cost because the OSPF cost value must be an integer. Consequently, because the default reference bandwidth is set to 100 megabits per second, all links that are faster than fast Ethernet also have a cost of 1. Reference bandwidth can be modified to accommodate networks with links faster than 100 megabits per second using the OSPF command auto cost reference bandwidth. This command must be configured on every router in the OSPF domain. The value is expressed in megabits per second. Therefore, to adjust the cost for gigabit Ethernet, you would use the command auto cost reference bandwidth 1000. You want to adjust it for 10 gigabit, you would do auto cost reference bandwidth 10,000. If you want to return it to the default, you would do auto cost reference bandwidth 100. As seen in this last bullet, you do have the choice to find the cost that will be used in the OSPF calculations with the interface command IP OSPF cost. The solution to managing the number of adjacencies and the flooding of link state advertisements on a multi-access network such as Ethernet or frame relay is the designated router. On multi-access networks, OSPF elects a designated router to be the collection and distribution point for link state advertisements sent and received. A backup designated router is also elected in case the designated router fails. All other routers become druthers. A druther is a router that is neither the designated router nor the backup designated router. Druthers only form full adjacencies with the designated router and the backup designated router in the network and send their link state advertisements to the DR and the VDR using the OSPF multicast address 224.0.0.6. If you were using IP version 6, that would be FF02::06. And you can see in the graphic there, without a backup, without a designated router or a backup designated router, the link state advertisement on an Ethernet network, like it's shown, would cause a lot of flooding in the network. So how are designated routers and backup designated routers elected? The following criteria are applied when electing a designated router and a backup designated router. First thing that will happen is the router with the highest OSPF interface priority will become the designated router. Don't forget, by default, they're all set to 1. So you would have to manually go in and change a certain router to a higher number so that it would be the designated router. The backup designated router would be the second highest OSPF interface priority. If you don't manually change the priorities, what's going to happen? If OSPF interface priorities are equal, the highest router ID is used to break the tie. This is the end of the OSPF single error review. If you are comfortable with these concepts, please listen to part 2 and 3 of this presentation. Thank you.